Every year, the world produces over 130 million tons of glass. But few people know that behind every clear window, bottle, or skyscraper facade lies a true symphony of fire, air, and light. Imagine a river of molten sand flowing over a mirror of tin, giving birth to perfectly flat sheets of glass so smooth they can reflect the clouds. But there's another kind of glass, one that's alive, with a soul, created by the breath of a craftsman and the fire of a furnace. Stick around to the end, and you'll see how ordinary sand travels through a 3,000-degree journey to become the transparent marvel our world is made of. While the vast majority of architectural glass today is born from a perfectly flat, fiery river flowing over molten tin in the float process, the true soul of the material is revealed in the methods that give it character and uniqueness. This journey from a simple, transparent sheet to a work of decorative art is a fascinating one. To create glass with individuality that carries the mark of a human touch, craftsmen still turn to techniques that have existed for centuries. A glassblower dips his long, hollow pipe into a furnace where a mass of sand and other minerals boils at 2,000 degrees Fahrenheit. He gathers a honey-like ball of glowing glass on the end of the pipe and, skillfully rotating it, begins to blow air into it. The initial bubble, born from his breath, gradually transforms into an elongated, shining hollow cylinder. Thanks to the force of gravity and skillful swinging, this cylinder can reach several feet in length. After the ends of the cylinder are cut off, it's sliced lengthwise and placed back in the furnace. There, under the heat, it slowly unrolls like a scroll, and the craftsmen smooth it into a flat sheet. Glass born this way is never perfectly flat. It's alive, retaining subtle waves, tiny air bubbles, and fine lines that tell the story of its fiery birth. This glass has a watery, organic quality that can't be replicated by a machine. But the creation of unique glass doesn't stop at forming the sheet itself. Other methods transform ordinary sheets into complex decorative elements. Fusing allows artists to literally paint with glass. Different colored pieces of glass are arranged on a base sheet and sent into a kiln, where at 1,500 degrees Fahrenheit, they melt together into a single piece, creating bright, painting-like compositions. Closely related is the process of slumping, or bending, where a flat sheet of glass is heated until it becomes soft and sags under its own weight, taking the shape of a ceramic or metal mold placed beneath it. This allows for the creation of curved panels and three-dimensional glass sculptures. Modern technologies add even more possibilities. Lamination allows for baking colored films, fabrics, or even thin sheets of metal between two layers of glass, creating endless variations of color and texture. Sandblasting and chemical etching remove the top layer of glass, making it matte and creating intricate patterns on its surface, from simple geometric shapes to photorealistic images. In this way, by combining ancient crafts with cutting-edge technology, modern production transforms simple glass into an expressive architectural material capable of shaping light, color, and space. In today's world, where tons of used glass containers are collected daily, the journey from the recycling bin to a new bottle isn't just remelting. It's a high-tech odyssey driven by computers and light. Imagine a mountain of crushed glass, dozens of feet high, where clear, green, and brown shards are mixed with labels, caps, and ceramic contaminants. Turning this chaos into pure raw material is a job for a whole complex of smart machines. It all starts with mechanical crushing, where steel hammers turn bottles and jars into fragments a few inches in size. This stream of glass, like a moving river, embarks on a journey through a labyrinth of sorting systems. First, powerful magnetic separators pull out any steel contaminants, and then eddy current systems literally shoot aluminum caps and foil into separate containers. Powerful blasts of air blow away light paper labels and plastic residue. But the hardest task is yet to come. Removing impurities that are almost identical to glass in weight and size, like pieces of ceramic, stone, or porcelain. These enemies of glass don't melt at standard temperatures and turn into defects in new products, so their removal is critically important. This is where optical sorting comes into play. The glass fragments are accelerated on a conveyor belt to high speed and fly through a scanning zone. For a split second, each fragment is illuminated by a bright light, and high-speed cameras take hundreds of pictures. A computer system, with lightning speed, analyzes the images, identifying foreign bodies by their transparency, structure, and shape. As soon as the system spots an opaque piece of ceramic, it instantly calculates its trajectory and commands a battery of air jets. A precise, sniper-like puff of compressed air knocks the unwanted element out of the mainstream, sending it to waste. This process is repeated thousands of times a minute. At the same time, an equally important sorting by color takes place. The same optical systems analyze the spectrum of light passing through each fragment. The machine distinguishes between crystal clear, rich green, and deep brown glass. Depending on the set program, the system can, for example, select only clear glass, knocking out all colored fragments with air jets, or separate the stream into 3 distinct color fractions. The result is a perfectly clean, color-sorted raw material, cullet, ready for a new life without any loss of quality, which is the pinnacle of the modern circular economy. This raw material can then be used to make flat glass. The birth of modern flat glass is a symphony of fire and precision, a spectacular process that turns ordinary raw materials into perfectly transparent sheets. It all begins in a massive melting furnace, the fiery heart of the plant that runs continuously for years. Into this furnace, which resembles a lake of molten fire, a carefully measured mix, or batch, is loaded, consisting of pure quartz sand, soda ash to lower the melting temperature, and limestone for stability. A significant amount of cullet, or crushed recycled glass, is added to this to help speed up the melting process. Inside the furnace, at hellish temperatures approaching 3,000 degrees Fahrenheit, these solid components slowly transform into a uniform, viscous liquid. The melting process is strictly controlled to ensure all particles are completely dissolved and gas bubbles are removed, creating a flawlessly pure melt. From the furnace, this stream of glowing orange molten glass, resembling a river of lava, flows smoothly into a bath of molten tin. This is the culmination of the process known as the float process. The tin bath, stretching for hundreds of feet, has a perfectly smooth, mirror-like surface. Since glass is lighter than tin and doesn't mix with it, it spreads out over the surface, forming a perfectly flat ribbon of uniform thickness. Gravity levels it from the bottom, and surface tension smooths it from the top, creating impeccable optical quality. The speed at which this ribbon is pulled from the bath determines its final thickness with pinpoint accuracy. After forming a perfectly flat surface, the glass ribbon, still very hot but now solid enough to hold its shape, enters the calmest but most critical stage, annealing. It enters a long tunnel known as an annealing layer. If glass is cooled too quickly, its surface will contract faster than its interior, leading to massive internal stresses that will make it brittle and prone to shattering. In the layer, however, the glass temperature is slowly and controllably reduced over several hundred feet, from over 1,000 degrees down to room temperature. This process allows the entire sheet, both surface and core, to cool evenly, relieving all internal stresses. From the other end of the layer emerges a single, flawless, continuous ribbon of perfectly transparent, stress-free glass, ready for automatic cutting into huge sheets that will become the windows, facades, and doors of our world. Every year, over 30 million tons of bamboo are harvested worldwide. But did you know that this seemingly ordinary grass can transform into steel, silk, and even concrete? It grows faster than any tree, absorbs more carbon dioxide than a forest, and doesn't require replanting. But the most interesting part is what's hidden inside its fibers. In this video, we'll show you how giant green stalks travel from plantations to ultra-durable flooring and delicate fabric. And if you watch until the end, you'll learn one shocking fact that will change your perception of the future of ecology. It all begins on vast bamboo plantations, covering millions of acres around the world. These are not chaotic thickets, but carefully managed farms. Unlike forests, bamboo does not require replanting. When one stalk, or culm, is cut, its extensive root system, called a rhizome, immediately sends up new shoots. This makes it one of the most sustainable resources on the planet. One plantation can yield harvests for decades without harming the soil. Moreover, a bamboo forest absorbs 35% more carbon dioxide and produces 35% more oxygen than an equivalent area of trees. Harvesters, armed with simple machetes or handsaws, selectively cut only mature stalks, whose age can be easily determined by color and texture. Young shoots are left to grow further, ensuring the continuity of the cycle. One such mature stalk can reach 60 feet in height and weigh over 100 pounds, making its transportation from the plantation to the primary processing plant a complex logistical task. When these green towers arrive for processing, their radical transformation begins. First, the long stalks are cut into manageable sections. Then, they are fed into a special machine that, with a deafening crack, splits the round sections into long strips. The next step is to remove the outer green skin and inner nodes, leaving clean, light bamboo planks. But inside these planks still lurks an enemy of durability: starch and sugar, which are a favorite food for insects and mold. To get rid of them, the planks are submerged in huge vats of boiling water or a hydrogen peroxide solution for several hours. This hot bath not only sterilizes the bamboo, but also washes out all the nutrients. After this, the planks are sent for drying. Some producers dry them in the open air, but for industrial scales, they are loaded into giant kiln dryers, where they spend several days until their moisture level drops from 50% to an ideal 8 or 10%. This stage is critically important, as any residual moisture can lead to warping and cracking of the finished product. But the journey from a 60-foot pole to a smooth floorboard requires even more impressive engineering. The dried planks pass through milling machines that give them a perfectly rectangular shape. Then begins a process similar to making industrial lasagna. To create horizontal flooring, the planks are laid in a single layer and glued under pressure. For vertical flooring, the planks are placed on their edge and pressed from the side, creating a denser pattern. But the real marvel is the strand woven technology. Here, the bamboo planks are not just glued together, but completely shredded into long fibers, mixed with an environmentally friendly resin, and loaded into huge steel presses. Under infernal pressure, reaching 3,000 pounds per square inch, and high temperature, this mass transforms into an extremely dense, monolithic block. The hardness of such flooring on the Yanka scale can exceed 5,000 units, making it more than 3 times harder than oak, and more resistant to scratches and dents than most traditional wood species. However, hardness is only one of bamboo's facets. Its other superpower is the ability to transform into something incredibly soft and silky. The process of creating bamboo fabric is a true industrial alchemy. The most common method, known as the viscose process, begins with grinding the bamboo raw material into a cellulose pulp. This pulp is then submerged in a sodium hydroxide solution and then carbon disulfide, which turns it into a thick, viscous liquid. This liquid, resembling honey, is forced under pressure through the finest holes of a metal plate called a spinneret. Imagine a microscopic shower. Emerging from the holes, the thin streams enter a bath of sulfuric acid, where they instantly solidify, turning into endlessly long fibers. These fibers are then washed, bleached, dried, and twisted into yarn, from which fabric is woven. Despite the complex chemical process, the final product is biodegradable and has unique properties. It is extremely soft, hypoallergenic, has natural antibacterial properties, and breathes wonderfully, making it ideal for clothing and bedding. The global bamboo market is colossal and is projected to exceed $100 billion in the coming years. Annually, over 30 million tons of bamboo are harvested worldwide, and this figure is only growing. From kitchen cutting boards and toothbrushes to construction scaffolding capable of supporting the weight of concrete and elements in premium class cars, this giant grass demonstrates its versatility. It is a testament to how nature, multiplied by human ingenuity, can offer sustainable, strong, and beautiful solutions for countless tasks, turning a fast-growing straw into the gold of the modern world. Bamboo grows both in the wild and on specially created plantations. Its natural habitat mainly covers tropical and subtropical regions of Asia, where it is an integral part of local ecosystems. At the same time, thanks to its unique properties and wide range of applications, bamboo is actively cultivated on plantations around the world. It is cultivated for the production of building materials, textiles, paper, interior items, and as a source of biomass. In the wild, there are over 1,000 species of bamboo. It is a perennial evergreen plant belonging to the grass family. Bamboo is known for its extremely fast growth. Some species can grow several tens of centimeters per day. Bamboo blooms very rarely, and after flowering and fruiting, the plant usually dies. Growing bamboo requires certain knowledge and care, including proper planting, regular watering, and choosing the right variety for specific climatic conditions. There are even ornamental types of bamboo that are grown in gardens and at home. Imagine this. Hidden right under your feet could be a mountain of old car tires. You'd think it's just rubbish, left to rot in a landfill for centuries. But what if I told you that this black rubber gets a second life and becomes the foundation for modern sports stadiums? Every single football field uses up to 40,000 tires. Now, multiply that by the more than 13,000 arenas in the US alone, and you get hundreds of millions of old treads, transformed from the road into a green carpet for athletes. How exactly new life is born from dirty scraps? We're about to break it down, step by step. Stick around till the end, and you'll uncover a secret most people never even thought to look for. So today, we're heading to a cemetery. A car tire cemetery. Acres of land piled high with mountains of black rubber rings. These are the silent veterans of the road, having done their thousands of miles, now lying here, seemingly useless. But this isn't the end of their story. It's just the beginning of their amazing reincarnation. We'll follow how these worn-out, dirty pieces of rubber go through a series of brutal, yet high-tech trials to be reborn as the soft, springy heart of a modern sports stadium. This is the story of how the roar of the road turns into the quiet whisper under an athlete's feet. Americans have learned to give a second life to the vast majority of tires. The recycling rate for old tires in the US is now over 85%. That's one of the highest rates for any consumer product. That means over 250 million tires a year dodge the landfill and are sent off for a new life. Some of them are burned as highly efficient fuel, some are used in civil engineering, but a significant and growing number are turned into that very same crumb rubber. In this tire cemetery, a machine that looks like a steel Tyrannosaurus Rex is at work. This is an industrial shredder. A huge loader grabs a whole handful of old tires and dumps them into the machine's steel jaws. Inside, two massive shafts with thick, sharp hooks spin with a deafening screech. They grab the tires with relentless force and, with an incredible crack, tear them to pieces. there's nothing delicate about it. The shredder's job is simply to break the tire's integrity, turning it into rough, palm-sized chunks. At this moment, the first important liberation occurs. Inside, every tire is a steel cord, a strong frame of steel wire. As the tire is torn apart, this cord is released, turning into a shiny web of steel threads mixed with rubber chunks. This chaotic mix of rubber and steel moves along a conveyor belt. And here, a powerful, massive industrial magnet spinning above the stream of shredded material comes into play. Like a fridge magnet, but a million times stronger, it pulls all the steel threads from the rubber mass. With a screech and a clatter, the steel cord sticks to the magnet and is dropped into a separate container. This steel will later be sent off to be melted down, while our cleaned rubber continues its journey. But it's still too big and coarse. The next stop is the granulator. This is something like an angry coffee grinder the size of a car. Inside, sharp blades spin at enormous speed, chopping the large chunks into a smaller fraction, about the size of a fingernail. During this process, another component of the tire is released, the textile cord. These are nylon or polyester fibers that gave the tire extra strength. These light, fluffy fibers need to be removed. To do this, the rubber granules pass through a system of vibrating screens and air separators. Powerful streams of air literally blow away the light textile fluff, leaving only clean, heavy rubber granules. Now we have a clean, but still quite large material. To become the surface of a stadium, it needs to be turned into a crumb. For this, the granules are sent for final grinding, often in what are called cracker mills. These are two massive, grooved steel rollers that rotate towards each other at different speeds. The rubber granules, falling between them, are not so much cut as they are torn and ground into the tiniest particles. As a result of this process, we finally get what this was all about: crumb rubber. It's a uniform, free-flowing mass, like black caviar or coarse sand, where each particle is only a few millimeters in size. This crumb is carefully sifted to ensure a perfectly uniform size, and is packed into huge one-ton bags. Its journey from a dirty tire to a clean, high-tech raw material is complete. And now, let's jump to the place where this black crumb will find its true calling: the construction of a new stadium. Workers roll out huge rolls of artificial turf over a perfectly leveled gravel base. This isn't just a green carpet. It's a backing with long, soft polyethylene blades sticking straight up. But for now, they look sad and limp, pressed against the base. For them to stand up and look like real grass, they need support. And this is where a special machine, looking like a large fertilizer spreader, drives onto the field. A process called infill begins. First, the machine spreads a uniform layer of fine, rounded quartz sand over the entire field. It's heavy and settles right at the base of the carpet, acting as ballast to keep the turf from shifting and helping to stabilize the blades. And following the sand, our main hero is spread onto the field, the black crumb rubber. The machine distributes it just as evenly over the entire surface, and here, the main transformation happens. This crumb fills the space between the blades, forcing them to stand vertically, just like real grass. Secondly, and most importantly, it creates a cushioning layer. When an athlete runs, jumps, or falls, this layer of billions of tiny, springy rubber particles compresses, absorbing the impact energy. It's like running on a billion tiny trampolines. This drastically reduces the strain on athletes' joints and makes falls much safer. The final touch is combing the field. A special machine with a huge brush drives over the turf, thoroughly mixing the sand and crumb rubber and brushing them deep down to the base, making every blade stand perfectly straight. And so, when the work is done, What stands before us is a perfectly green, resilient, and safe field. And none of the players running on it might ever guess that under their feet, between the bright green blades, lie millions of particles of old car tires that have completed their epic journey from the roar of the motorway to the quiet, springy surface of a sports arena, having received a second, much nobler life. To create one standard American football or soccer field, you need, on average, between 20,000 to 40,000 old passenger car tires. Just think about it. A single field completely eats up a whole mountain of rubber waste. And how many of these fields are there in the country? Right now, there are over 13,000 artificial turf fields in the US, at schools, colleges, parks, and professional arenas. And that number is growing every year. Now for some simple maths, even if we take the minimum figure of 20,000 tires per field, it turns out that over 260 million old tires have found their new home in the surfaces of sports fields across the country. That's almost a year's supply of all the rubber scrap the country generates. Natural grass is a very fussy thing. It needs to be constantly mowed, watered, fertilized, and given time to rest. On average, a natural field can handle no more than 20 hours of play per week. And an artificial turf field, it can operate 24 hours a day, 7 days a week, in rain or shine. Now, let's talk about water. A single artificial turf field can save from 500,000 to 1 million gallons of water every year. That's the amount of water an average family uses in several years. Add to that the savings on fertilizers, pesticides, and lawnmower work, and the benefit becomes obvious. So next time you see a bright green field, know that it's not just a place to play. It's a monument to human ingenuity that solves a waste problem, makes sports safer, and saves precious natural resources, one old tread at a time. Imagine a magnet so powerful it can lift a weight 1,000 times its own. How can a piece of metal stop a jet engine turbine or become the heart of a Tesla electric motor? The secret lies in rare earth elements, materials that hide more mysteries than gold or platinum. To create a single neodymium magnet, you have to move mountains of ore, melt metal at over 2,700 degrees, and use technologies that resemble alchemy. But there's a detail that almost no one knows about. Watch till the end, and you'll learn a secret that will change your understanding of the power of metal. The mining and initial processing of rare earth ores are a key stage in the production of neodymium magnets, as this is where the foundations for obtaining the necessary components are laid. This process begins with the large-scale mining of ore, containing the rare earth elements that make up neodymium. In the first stage, the ore is extracted from the earth using various mining methods. This can be either open pit mining or underground mining, depending on the depth and type of the deposit. After extraction, large chunks of ore are delivered to crushing plants. At the crushing plants, the ore undergoes primary crushing. Large boulders of ore pass through a series of crushers that gradually reduce their size into smaller fractions. This is necessary for further effective processing and extraction of valuable components. The crushed ore may then be fed into mills for further fine grinding into a powder or a pulp, which consists of fine ore particles suspended in water. The next critically important stage is ore enrichment, the purpose of which is to separate the rare earth minerals from the waste rock. This process can involve various methods. One of the most common methods involves mixing the crushed ore with water and special reagents. These reagents selectively attach to the surface of the rare earth minerals, making them water repellent. Air is bubbled through the mixture, creating bubbles to which the hydrophobic minerals adhere and rise to the surface, forming a froth that is then collected. Heavier particles settle faster, allowing them to be separated from the lighter ones. Some rare earth minerals have magnetic properties, which allows them to be separated from non-magnetic components using magnetic separators. After enrichment, a concentrate is obtained, which contains a much higher concentration of rare earth elements. However, this concentrate is still not a pure metal. It requires further chemical processing, which usually includes dissolving the valuable components with acids or alkalis, precipitation, solvent extraction, and ion exchange chromatography. These processes allow for the separation of each rare earth element individually and its purification to a high degree. For example, neodymium is separated from other rare earth elements like praseodymium or samarium. The final result of this complex chain of processes is the production of high-purity neodymium oxide, which is then reduced to metallic neodymium. This metallic neodymium, in the form of granules or ingots, is ready for the next stage, alloying with other components to create powerful neodymium magnets. The entire process requires strict quality control and significant energy expenditure, but is absolutely necessary to obtain the raw material for the production of these strategically important materials. After the careful extraction and purification of rare earth elements, particularly neodymium, comes one of the most crucial stages in the production of high-performance neodymium magnets: alloying. This process demands extreme precision and control, as the final microstructure and, consequently, the magnetic properties of the finished material depend on it. The purified metals, neodymium, iron, and boron, are carefully weighed in strict proportions. These three elements are the main components of the alloy, providing its unique magnetic characteristics. In addition to them, small amounts of other elements, such as dysprosium, terbium, cobalt, or copper, may be added to the alloy. These additives are introduced to achieve specific properties, for instance, to increase the magnet's temperature stability, improve its resistance to demagnetization, or modify the material's brittleness. The exact composition of the alloy is a trade secret for many manufacturers and varies depending on the desired final characteristics of the magnet. The weighed components are placed in a specialized vacuum induction furnace. The use of a vacuum is critically important as it prevents the oxidation of the rare earth metals and other components at high temperatures. Oxidation would lead to the formation of undesirable phases, which would degrade the magnetic properties of the material. Induction heating ensures rapid and uniform melting of all components, creating a homogeneous melt. The melting temperature in such a furnace can reach over 2,700 degrees Fahrenheit. After achieving a complete melt and homogenization of the alloy, the stage of rapid cooling, known as the strip casting method, begins. This is a key moment for forming the optimal microstructure. The molten metal is poured in a thin stream onto a rapidly rotating, cooled drum. Contact with the cold surface of the drum leads to an extremely rapid cooling of the melt at a rate of up to millions of degrees per second. This extremely rapid cooling prevents the formation of large crystal grains and allows for the formation of an amorphous or microcrystalline structure. Instead of the typical crystalline structures formed during slow cooling, extremely fine grains are formed. This process is also known as rapid solidification, and it is fundamental to achieving high magnetic properties. The resulting material takes the form of thin, easily crumbled flakes or ribbons. This unique microstructure, with very fine, often anisotropic grains, is the key to the high strength of neodymium magnets. The smaller the grain size, the more difficult it is for the magnetic domains to change their orientation, which provides high resistance to external demagnetizing fields. Thus, the alloying and rapid cooling stage is fundamental for forming the magnetic characteristics that will later be locked in during subsequent production stages. After the alloying and rapid cooling stage, when thin flakes or ribbons of the neodymium iron boron alloy have been formed, a stage called hydrogen decrepitation begins. Then there are two paths: either long-term dry storage in double-walled concrete containers or reprocessing. That happens in other countries, as the US mostly stores rather than reprocesses. In dry storage, the assemblies stand for decades, cooled by natural ventilation, as if in a nuclear monastery. This isn't the end, but a new stage of life, slow, controlled, but deeply connected to the future of energy. Because even after the reactor, this fuel remains a source of heat, a lesson, and a reason for respect. Transportation is under guard on a special route with an escort, GPS, and mandatory 2 seals, 3 codes, and a dosimeter on every side. Because even in its peaceful form, this is dangerous stuff that commands respect. After all is said and done, what's left is the depleted uranium hexafluoride. They call it tails. It's a mix of isotopes that still has a little U-235, but not much. These tails are stored in steel barrels, in special supervised yards. But in the future, they could be reprocessed in next-generation reactors, squeezing out every last drop. When a fuel assembly has served its 4 or 6 years in the heart of a reactor, it's no longer the shiny star it was at launch. It's removed, carefully by a robotic system, and moved into pools of water. The depth is over 20 feet. The water cools it and shields the radiation because the fuel is still hot, both physically and radioactively. There it rests for several years. Next, the pellets are sintered in furnaces at almost 3,000 degrees to make them as strong as porcelain. Then they're polished and ground. Perfect dimensions are crucial for a tight fit inside the cladding. The pellets are loaded into long metal tubes. Fuel rods, usually made of a zirconium alloy because it doesn't rust, doesn't react with water, and can withstand insane radiation. Each rod holds over 300 pellets. The rods are hermetically welded shut and bundled into modules, fuel assemblies. They look like a frame of several dozen tubes gathered into a square. One such assembly can weigh over 1,500 pounds and works for up to 6 years in a reactor. After assembly comes testing for leaks, uniform filling, weld integrity, and behavior under temperature. There are no small details, because any one of them could cost not just money, but lives. The finished fuel is packed into armored containers that can withstand impacts, fires, and falls from a height. But one centrifuge isn't enough, so they're connected in cascades of hundreds, sometimes thousands. Each one slightly enriches the gas, then passes it to the next. And so it goes, cycle after cycle, until the U-235 content reaches at least 3 or 5%. That's the reactor-grade standard. For weapons, of course, they follow entirely different routes, which are classified and under strict international control. Okay, the gas is enriched, but you can't feed a reactor with a gas. So now it's converted again, this time into a solid ceramic form. After a series of chemical reactions with hydrogen, oxygen, and ammonia, the gas becomes uranium dioxide, a solid substance with a dark grey color. This powder is pressed under 20 tons of pressure into small cylindrical pellets, 3/10 of an inch in diameter. They look almost cute. But each of these little pills holds an energy equivalent to 17,000 cubic feet of natural gas. And so, mission accomplished. The dust has been turned into a gas, ready for the most interesting part, isotope enrichment. But don't get too excited yet. This gas is like a wild cobra. Beautiful, shiny, but if it bites, no one can save you. You think a washing machine spins fast? You haven't seen nuclear centrifuges that do 70,000 revs a minute. That's 10 times faster than a jet engine turbine. And all for one thing: to separate uranium isotopes. Uranium hexafluoride, that same toxic gas we just made, is pumped into a tall, narrow cylindrical chamber which is spun up to an insane speed. Centrifugal force does its thing. The heavier U-238 atoms are flung to the edge, while the lighter U-235 atoms stay closer to the center. A tiny microscopic difference, 1% in mass, and all this explosive technology spins just for that. That means you just need to heat it a little, and it turns from crystals into vapor. But it's not that simple. It's extremely toxic. It corrodes metals, destroys skin, and in moist air, it instantly turns into hydrogen fluoride and uranic acid, basically a deadly cocktail. That's why this is all done in sealed, automated reactors that look more like devices from an evil genius's lab. Temperature, pressure, ventilation, everything is under control. Workers sit behind thick windows, watching the gauges. Any mistake, boom or hiss, and you're in a hazmat suit scrambling for the decontamination shower. This substance forms as solid whitish crystals when cooled to room temperature. These crystals are stored in steel containers, drums with engravings, batch numbers, and a radioactive sign. Each one weighs up to 14 tons. Yellowcake is packed into double-walled drums, loaded onto escorted trailers, plastered with radiation signs, and off it goes to an enrichment plant. It's from this toxic dust that the journey begins, the one that leads to the white light of a lamp over your kitchen table, or the electricity in the subway hurtling beneath New York. Right then, the yellowcake has arrived, in drums, radioactive and dry as a desert wind. The next step, turn it into a gas. And not some lavender-scented air freshener, but uranium hexafluoride, the very same stuff from which the required isotope for reactors and other things is later separated. Let's cook, baby! The uranium concentrate is first dissolved in acid, purified, filtered from impurities, converted into uranium dioxide. And this is where the magic starts. The uranium dioxide is treated with fluorine in special reactors at a temperature of 1,000 degrees. And as a result of the reaction, a volatile, transparent gas is formed, which boils at 133 degrees. The rest is mostly useless mass that doesn't work in a reactor. And to squeeze the required drop of energy from it, hundreds of tons have to be processed. That's why they say nuclear energy is quite the marathon. After mining, the ore is crushed, milled, and thrown into a chemical bath. Acid or alkaline solutions are added, which extract the uranium like coffee from a filter. Then comes filtering, precipitation, and drying at 500 degrees. And what comes out is yellowcake, a yellow powdered concentrate. The official name is natural uranium concentrate, but everyone at the plants just calls it yellowcake. It looks pretty, mustard-colored, fluffy, like a spicy powder for a Barbie. But God forbid you breathe it in or touch it. Alpha radiation, a long half-life, dangerous dust that gets into your lungs and settles there forever. It's handled only with respirators, suits, and behind 3 layers of glass shielding. It all starts in the dust. And that's not a figure of speech. Uranium ore is mined in hot, arid regions. Arizona, Wyoming, Texas, New Mexico. Think cowboy country, but instead of lassos, they have drill rigs, and instead of a sheriff, engineers in anti-radiation suits. The sun here is a scorcher, up to 100 degrees Fahrenheit in the shade if you can find any. There are 2 ways to get it. Open pit mining, where they strip the topsoil and haul the ore out with excavators, and underground mining, with explosives, lifts, and ventilation that howls like an old tractor. Then there's the in situ leaching method. Pipes are driven into the ground, special solutions are pumped in to dissolve the uranium straight from the rock, and then it's all pumped back out. All this ore, a gray-brown rock, looks no different from ordinary stone. But inside it, uranium-235 makes up only 0.7%. What could be scarier than dust that glows with an invisible light? A rock that looks like ordinary gravel, but holds the fuel for power stations that light up megacities. So why is uranium called an energy marathon? Because to get just a few grains, you have to move hundreds of tons of earth, boil ore in acids, and turn it into a yellow powder that can kill with a single touch. And this is where the real alchemy begins. Toxic dust becomes a gas, and that gas becomes energy. But there's a detail they don't talk about publicly, and you'll only find it out at the end of this video. Every year, millions of tons of chemicals are produced worldwide, but one of them, chlorine, is truly staggering in scale. In the United States, over 12 million tons of this gas are made annually. That's the same weight as 120 Gerald R. Ford aircraft carriers, the heaviest ships in the world. But where does this dangerous, yet vital substance come from? It all starts not in a lab, but in underground deposits of common salt. From there, it involves electricity, membranes, and an entire industry that consumes more power than entire American states. And if you watch till the end, you'll discover the secret that chlorine hides behind its sharp smell. The United States is one of the world's largest producers of chlorine. Each year, plants in the country produce over 12 million tons of the gas. This number is just hard to wrap your head around. Imagine the weight of the aircraft carrier, the Gerald R. Ford, the heaviest warship in the world. It's about 100,000 tons. This means that in a year, American industry produces as much chlorine as 120 of those aircraft carriers weigh. This enormous quantity makes chlorine one of the top 10 most produced chemicals in the country. It all begins not in a laboratory, but deep underground. The main ingredient for our recipe is common rock salt, or sodium chloride. But it doesn't arrive at the plant in salt shakers. It's either mined in the form of huge chunks, or, far more efficiently, pumped out from under the ground. Water is pumped into deep underground salt deposits. The water dissolves the salt, creating a saturated salt solution called brine. And it's this concentrated, salty as tears solution that is our raw material. But it's still impure. It's full of contaminants, calcium, magnesium, and other minerals that can clog up our expensive equipment. So before the main show begins, the brine goes through a thorough purification process. It's passed through a whole series of tanks where chemicals are used to precipitate and filter out all the impurities. What comes out is a perfectly clean, clear, and very salty solution, ready for the main event, electrolysis. Now, let's head to the heart of the plant, the so-called cell room. This is a huge loud hall filled with rows of strange enclosed tanks connected by a network of pipes and thick electrical cables. These are the electrolyzers, or cells. This is where all the magic, or more accurately, all the chemistry will happen. Let's imagine one such electrolyzer. Essentially, it's a box into which our pure salt solution is poured. And into this solution, two electrodes are submerged, a positively charged anode and a negatively charged cathode. Now, a direct electric current of colossal power is applied to these electrodes. And this is where the split begins. The salt molecule in the water breaks down into positively charged sodium ions and negatively charged chloride ions. The electric field forces them to move. The positive sodium ions are drawn, as if by a magnet, to the negative cathode, and the negative chloride ions to the positive anode. And it's at the anode that the whole point of the process occurs. Each chloride ion that sticks to the anode gives up its extra electron. Two such chlorine atoms, having lost their charge, immediately pair up, forming a molecule of chlorine gas. Billions of these molecules gather, and tiny bubbles of a greenish-yellow gas begin to appear on the surface of the anode. This is our chlorine. The main resource for chlorine production is electricity. The chlor-alkali industry is one of the largest consumers of electricity in the entire US manufacturing sector. To produce 1 ton of chlorine, it takes about 2,500 kilowatt hours of electricity. Now, multiply that by 12 million tons a year. It turns out that this industry consumes about 30 billion kilowatt hours annually. That's more than the annual electricity consumption of entire states, like Vermont or Wyoming. It's like an entire city of 1 million people, working year-round just to split salt molecules. But what's happening at the cathode? The sodium ions have drifted over there. But they don't turn into metallic sodium. Instead, the electric current splits the water molecules in the solution into hydrogen and hydroxide ions. Bubbles of pure hydrogen are released at the cathode. That's our first byproduct. And the hydroxide ions left in the solution combine with our sodium ions to form sodium hydroxide, or caustic soda. This is our second, incredibly valuable byproduct. But here, a huge problem arises. We've just created 3 substances: chlorine, hydrogen, and caustic soda, and they must never be allowed to mix. Chlorine and hydrogen together form an explosive mixture, and chlorine and caustic soda react to form bleach, which is not what we want at all. So, the genius of the technology lies in separating these 3 products at the very moment of their birth. This is done using special membranes or diaphragms. Imagine a thin, paper-like, but very clever partition standing between the anode and the cathode. This membrane, made of a special polymer, is like a bouncer at a nightclub. It allows the positive sodium ions to pass through to the cathode, but blocks the negative chloride ions, preventing them from getting into the cathode space. This way, chlorine is born and collected in one part of the cell, while hydrogen and caustic soda are in another. Now we need to collect our harvest. The moist, hot, greenish-yellow gas is continuously pumped out of the anode chamber. First, it needs to be cooled. It's passed through heat exchangers where it gives off its heat. Then, it needs to be dried. Chlorine is incredibly aggressive, especially when wet. It corrodes almost everything. But there's one substance it doesn't touch: concentrated sulfuric acid. So, the wet chlorine is passed through towers where it bubbles through sulfuric acid, which, like a sponge, absorbs all the water from it. The resulting dry, cool, but still gaseous chlorine is ready for the next stage: liquefaction. It's compressed under enormous pressure and cooled at the same time. Under this double whammy, the gas turns into a clear, amber-yellow liquid that looks like oil. This liquid chlorine is much easier to transport and store. It's poured into special thick-walled steel tankers, or rail cars. Every step of this process is carried out under completely sealed conditions, because a leak of this gas is deadly. And what about our byproducts? They are no less important. The hydrogen we've produced is collected, purified, and used either as fuel for the plant itself, or sold for ammonia production, or in the food industry. And the resulting caustic soda solution is pumped out, concentrated by evaporating the excess water, and sold. It's one of the most important products in the chemical industry, used to make soap, paper, aluminium, and much more. And so, from simple salt water, by passing a huge amount of electricity through it, we learn to obtain 3 extremely important substances at once, which form the foundation for thousands of other products that surround us in our daily lives. Now let's see where all this enormous amount of chlorine goes. You might think it all goes into disinfecting swimming pools, but that's just a drop in the ocean. In fact, less than 5% of all chlorine is used for water disinfection. So where does the other 95% go? It's a key building block for other products. About 40% of all chlorine goes into the production of this universal plastic. The vinyl windows in your house, water pipes, medical IV drips, vinyl records, the credit card in your wallet. All of these were born thanks to chlorine. Another 40% or so is used to create thousands of other organic and inorganic compounds. Pharmaceuticals, solvents, refrigerants, herbicides, insecticides. The list is endless. Chlorine is also a key component for bleaching paper, giving it that clean white color. And finally, about the byproducts, which are actually no less important. We remember that for every ton of chlorine, we get about 1,100 tons of caustic soda. This means that American industry produces over 13 million tons of this vital alkali annually. This makes chlor-alkali production a perfectly balanced business. When the demand for one product falls, the demand for the other can rise, allowing plants to operate stably. So these millions of tons are not just statistics. They are proof that this sharp, suffocating gas is the invisible foundation for a huge part of the American economy. From the plastic pipes under our streets to the medicines in our pharmacies. Every year, billions of square feet of concrete are born in the world, but only a few know about the material that has turned construction on its head. Imagine this. In a single shift, one machine can create almost half a mile of slabs, and the annual output in North America is over 200 million square feet. That's the area of 30 pentagons. How do these lightweight slabs, weighing thousands of tons less, support entire buildings? The secret is hidden in their steel muscles and the mysterious voids inside. Watch till the end, and you'll discover something most people don't even have a clue about. The slip former machine crawls along a 600-foot casting bed at a speed of about 4 feet per minute. Doesn't sound too quick? Well, let's do the maths. That's 200 feet an hour. That's almost the length of an Olympic swimming pool, born from concrete in less than an hour. In a single 10-hour shift, one of these beds can churn out nearly half a mile of perfectly formed concrete slab. And a big plant might have several of these beds. This isn't just building, it's a conveyor belt running at a speed unthinkable for traditional, pour-on-site concrete. And now for the main trick, the hollow cores. These holes inside aren't just for looks. They slash the slab's weight by almost 50% compared to a solid slab of the same thickness and strength. What's the payoff? Picture this. You're building a 100,000 square foot office block. If the floors were made from standard, solid concrete, they'd weigh about 5,000 tons. But with hollow core slabs, just 3,000 tons. We've just stripped 2,000 tons of dead weight from the building. That's the weight of about 500 adult elephants that the foundations, columns, and beams no longer have to carry. This allows the entire structure to be lighter, more slender, and most importantly, a whole lot cheaper. But how can such a light slab be so strong? The secret is in those tensioned steel muscles. The concrete used in these slabs isn't what you'd find on the footpath. It's high-strength concrete that can handle pressures over 8,000 pounds per square inch, while standard concrete manages only 3,000 or 4,000. And the steel strands inside are tensioned with such force that they create a constant state of compression within the slab. Because of this, a hollow core slab can easily span 60 feet with no intermediate support at all. 60 feet. That's the width of a professional basketball court. Imagine a huge open space with not a single column in sight. That's exactly why these slabs are a favorite for building car parks, supermarkets, and open-plan offices. Every year, over 200 million square feet of hollow core slabs are produced in North America. The number is just staggering. It's enough area to build 30 colossal buildings like the Pentagon. Every single year. This isn't just a building material. It's an entire industry built on speed, efficiency, and clever use of resources. So these figures aren't just dry data. They're proof that sometimes, to get stronger, you just have to get rid of the unnecessary stuff on the inside. It all starts not in a concrete mixer, but on a massive, perfectly flat runway inside the workshop. This is the casting bed. Imagine a perfectly smooth, polished steel track a few feet wide, but 600 feet long. That's longer than 2 footy fields, end to end. Beneath this track run pipes circulating hot water or steam to keep it warm. This is the perfect cradle for the birth of our future giant. At both ends of this track stand massive steel abutments, anchored into a thick concrete foundation. They're like steel teeth sunk into the earth, and their job is to withstand simply inhuman loads. Between these two abutments, high-strength steel strands are stretched. This isn't your average wire. It's several steel filaments twisted together, each capable of holding the weight of a car. They are laid out along the entire 600-foot length of the bed, forming the slab's future skeleton. One end of each strand is securely fixed in an abutment. The other is hooked up to a giant hydraulic jack, and this jack starts to pull. It tensions each of these steel strands with a force of 30 or 40,000 pounds. That's like hanging 3 full-sized utes off each thin strand. The steel muscles tense up, becoming as taut as the strings of a giant guitar, storing a colossal amount of energy. This is secret number 1, pre-stressing. When the steel skeleton is strained and singing with tension, the star of the show appears, the slip former. This is one of the most incredible machines in the construction world. Imagine a strange, low-slung, self-propelled creature, slowly crawling on rails along our long bed. It has a large hopper on top, which is filled with concrete. But this isn't your typical liquid concrete. It's what's known as zero-slump concrete. It's so dry it looks like damp earth. If you picked it up, it wouldn't flow through your fingers. And so, this machine begins its slow journey. Inside, a real marvel takes place. Firstly, the concrete from the hopper is fed downwards, enveloping our tensioned steel strands. Secondly, special vibrators and compactors ram this dry mix with incredible force, making it unbelievably dense. And thirdly, and most importantly, inside the machine are special forming tubes, or mandrels, which vibrate as they push through the concrete, leaving behind perfectly round, smooth voids. The machine, like a giant concrete snail, slowly crawls forward, leaving in its wake a perfectly formed, endless concrete slab with hollow cores inside and tensioned steel muscles hidden within its body. Because the concrete is so dry, it holds its shape instantly and doesn't sag. This is secret number 2. The voids, which make the slab 50% lighter than a solid one while barely reducing its strength, as the top and bottom sections do most of the work. Once the machine crawls to the end of the 600-foot bed, its job is done. But our slab is still green and weak. It's time for a spa treatment. Workers cover the entire length of this concrete ribbon with huge insulating tarps, like blankets. Hot steam is then pumped under these blankets. This creates a sauna effect, which dramatically speeds up the chemical reaction of the concrete curing. Under normal conditions, concrete needs weeks to reach its full strength. But in this hot, humid atmosphere, it achieves the required strength of over 5,000 pounds per square inch in just 12 to 24 hours. When the concrete has set and become hard as rock, it's time for the release. Workers slowly let off the pressure on the hydraulic jacks. The tensioned steel strands, now permanently bonded to the concrete, try to shrink back to their original length. But the concrete won't let them. As a result, this massive compressive force is transferred to the concrete slab itself. Now it's not just a concrete slab, it's pre-stressed or compressed. This means that when a load from above tries to bend it, it first has to overcome this built-in compressive force. This is what allows it to span huge distances without extra support. And the final act of this performance, the cutting. A giant saw travels on rails along our long concrete ribbon. It's a monster with a massive blade coated in industrial diamonds. With a deafening roar and a spray of sparks and cooling water, this saw cuts the slab with incredible precision into sections of the required length, according to the order. The finished, perfectly flat, lightweight, and incredibly strong slabs are then picked up by giant cranes and loaded onto trucks. And just like that, after a journey from a tensioned steel string to the slow crawl of a concrete snail and a final diamond cut, this brilliant piece of engineering is born, ready to become the fast, efficient, and reliable flooring in the buildings where we live, work, and play.